Hi there, welcome to the first video for Chapter 8, so on modelling. This is our first kind of proper mechanics unit of Year 1, and this is where we're going to start looking at how we can model particular mechanics situations and what we can learn from those models. This particular video is going to talk about algebraic modelling. Now before we do that, I wanted to make sure that we were really clear on what on earth a model actually was. And so I just wanted to make it, to clarify that when we are modelling, that it is a process of simplifying a situation. If we talk about having a model of a situation, what it means is that we have simplified it to some extent. I've made some what we call simplifying assumptions. Once we've made those assumptions, it will allow us to make more easily make calculations about that situation. And importantly, we'll try and maintain some validity of those results. I don't want to be in a situation where I've modelled something I'm interested in and left myself with results that don't make sense in the original context because my assumptions removed any key details. We also will use models primarily to look at specific inputs and what happens when we vary them. Okay? Because of that, it means that modelling is really a form of experimentation that we'll use in maths and in other subjects, and it allows us to kind of describe and explain phenomena in the world around us. That means that modelling is used in lots of different studies or fields of study, from the social sciences all the way through to the natural or pure sciences. Now, when we make models or when we model things in both of those kind of fields, what we're looking for is to be able to draw some conclusion about the situation in which we're modelling or the thing that we are modelling. And I thought it might be useful to have a look at a quick example of that, or of a kind of famous model really that's used quite a lot to describe something. Now, this is obviously a picture of someone buying some fruits, but the situation in terms of kind of making any predictions or understanding the situation is relatively difficult. We don't have too much of an idea of why this person might be selecting a particular fruit. We also don't really have that much clarity on why the fruit is priced the way it is by the shop, and so this person is making a decision or interacting in the world around them in relatively a complex situation. Now, there's a very famous model about this kind of thing, about an economic transaction, which simplifies this to the point where we can make some conclusions about the way in which economics works, or the way in which pricing especially works, and that's the supply and demand curve model. Now, supply and demand suggests that the price point in a marketplace is set by an interaction between both the supply of a particular good and the demand for that particular good. So going back to that particular kind of image of someone buying fruit, if we have a real glut of apples, or a real kind of overproduction of apples, that increase in supply may well push the price down because there are more apples than people actually desire. If for some reason the supply drops, there's a bad crop, this may well push the price of those apples up because those that are available are more sought after. So the demand would be outstripping the supply. Now, this very simple model of how in which prices are arrived at in the marketplace, and some sense of our equilibrium point, the plot price, which is the point which is labelled here, allows us to draw conclusions about something which is relatively complex, while maintaining some validity and some kind of fidelity with the original situation. Now, what we need to be able to do in maths, and what we'll do as throughout this unit, is look at kind of models in a more kind of mechanical sense. But the model will work in a similar way in which we've made assumptions about the particular situation to draw a conclusion from it. So let's look at a more mathematical answer, a more mathematical example. Let's say we have a mathematical model of a percentage return on an investment, which is given by R, and it's given by the equation R of t equals a quarter t squared minus 2t plus 6. Now, we've used function notation here, R of t, particularly so it shows us the interaction between these two variables. I've got a percentage return on investment, which is given by R. Now, R is dependent upon T, where T is the number of years after the investment was made. Now, one thing I'm always going to suggest when we're looking at these is that on your calculators, you graph each of these functions. Okay, so for this particular example, I've done it for us, and I've found us a graph of this particular function. So this is R of t, with R on the y-axis, t on the x-axis. Okay, we've got a quarter t squared minus 2t plus 6, obviously a positive quadratic curve. Now, this particular model at the moment, in the pure kind of mathematical form of its curve, makes some sense to us. We can see that that we've got a return of investment at various points along that curve. The challenge for us, though, is that actually we need to put some limits on this particular model, because I've got a situation over here where I've got negative values for the time. Now, where t is a number of years after investment was made, that means I'm not going to have any negative time. So actually I need to restrict this and say that t is always greater than 0 for this particular curve, for this particular model. Now, this will be a very, very common thing to see, that there may well be limits on the way in which, or that limits on the inputs for a particular model, and those inputs may well be defined by the context. So in this particular regard, we can't have negative time, or they could be defined by the maths itself. That's something we'll have to investigate and define for ourselves. Now, what we may get asked occasionally is to, for instance, find the percentage return on the investment after 8 years. Now, this question is asked in the context of the original question. Okay, so we need to be able to decode that, collect the information, and then find information from our question. So we've got a time period here of 8 years, so we can say that t equals 8, and then we could try and find the percentage return. Now, we can see here I've got t equals 8 down here on my x-axis, and so I can quite easily read off the graph. Now, that obviously depends upon having an accurate graph drawn, which we might not always do. So a much quicker and much easier notion is actually just to substitute our value in. So I can find r of 8. I can plug my numbers in and I'm going to get a value of 6, which makes sense for us here, as this graph is accurately drawn. So using this model, I can define or find something and predict something about the return of an investment, the percentage return at 6% after 8 years. Now, that obviously tells me something here, and I have to be careful, as we've said, to make sure that I'm putting in any value of t which is within the limits of that model. So t is greater than 0. I'm going to go through one more example for us to have a look, and then we're going to go onto the sheet itself. This particular model is looking at the motion of a football after a goal kick. Okay, it's modelled by the equation h lots of x equals negative 100th x squared plus 3 over 2x. And here we're given that h is the height of the football and x is the horizontal distance travelled, and they're both in metres. Now, what I'd suggest you do now is, using a calculator, is graph that function, have a look at what it looks like. Now we've got a negative x squared graph. And it's important to have a look at that graph because it will help you to look at the way in which that ball is moving. So we've got h is the height of the ball, and x is the distance travelled horizontally. And we've got 3 questions to look at. I want to calculate how far the ball travels before it bounces. I want to define the range of values of x for which the model is valid. I want to comment on the validity of the model. Now, for part A, a really important thing is that we need to think about what this question is asking us in the context of the model. I'm being asked how far the ball travels before it bounces, so I need to think about which one of my inputs may well be at a specific point, may I know something about when it bounces. Now, when a ball bounces, we know that the height of that ball above the ground must be 0. Okay, it must contact the ground, and therefore the height will be 0. That allows me just to substitute h is 0 into my equation, and then I'm left with a quadratic I can solve. I can either factorise it as I've done, or I can plug it into my calculator, and I'm going to get 2 figures. X is 0 or x is 150. Now, at this point we can kind of sense check our answers quite easily. Now, we've got two answers here. Both of those answers are valid and both of those answers are true. The key thing that I need to be aware of, though, is that in actual, I want it to make sense in the context of my model. So I've got x is 0, okay, when h is 0. Now this makes some sense because actually that's just going to define my starting point of the ball. Okay, x is 0 when h is 0. So at the point at which the ball is at its before it is kicked, and it's been placed by the goalkeeper, it's at the point h0, x0. And so I'm forced to conclude then that the distance travelled is 150 metres before it bounces. Now for part B, I want to define the range of values for which the model is valid. Okay, the range of values of x for which the model is valid. This question is asking me to have a think about what the function looks like in its kind of total form and see if there's anything in there that would lead us, or any values that we need to restrict, because they may well lead us to a result that may well be unintuitive or may well go against our experience of the world. Now hopefully you're looking at that graph on your calculator at the moment, and we'll see that past x equals 100 and kind of greater than x is 100 or less than x is 0, we're going to have a graph that is below the x-axis and leaves us with negative values of height. Now this is difficult for us because I've got an idea that height is above the ground, the height of the football above the ground, and that means that my height really must be a positive value. So having a negative value for height doesn't quite make sense for me, and so I'm going to restrict my values of x from 0 to 150. Okay, so this model is valid for values of x between 0 and 150 metres. So it will not be valid after my ball has bounced, but it can be valid up to the point at which it touches the ground. And then part C. Now this is a key thing here. I want to comment on the validity of the model. When we're asked this, it's really looking for any reason why we should discredit this model. Is there anything about this that just doesn't quite make sense? And for part C, I'm going to suggest that there is. The challenge here is to think about the actual context. Let's go back to part A and think about the context. This model is telling me that a goalkeeper kicks the ball and it doesn't bounce for 150 metres. Now, some of this can be difficult because it will depend on our own experience, but realistically, that seems improbable. 150 metres is a really, really long way. That is, in actual fact, longer than a football pitch. So our model suggests that a goalkeeper has kicked the ball about 1.5 times the length of a football pitch before it bounces, which suggests to us that actually the model is not an accurate one. And so we should potentially be rethinking how we model this particular motion. Next step is to have a look at the pre-quiz, which is available for you, and then get started on sheet 1. Good luck.